Okay, so we'll get started and continue from where we got up to in yesterday's lecture. Okay. Okay, so just to recap very, very briefly, because it was only yesterday, okay, what we'd done was we'd combined this source with this uniform flow. Is this too loud, or you can hear me? It sounds pretty weird from where I am. Okay, so we'd come up with this half-ranking body, which was just a source placed at the origin and a uniform flow, and we replaced the curved separatrix associated with that body with a solid boundary, which is this grey shaded region on this figure. And then in yesterday's lecture, what we were trying to do was nut out the pressure force acting on that solid surface. Okay, so what we really did was we derived this version of Bernoulli's equation, and we had this very kind of happy result that for irrotational flows, Bernoulli's equation is actually applicable between any 2 points in that flow field. Okay, so where you're used to being able to or you should be used to only applying Bernoulli's equation along a streamline, although you'd all conveniently forgot that. For irrotational flows, you can apply Bernoulli's equation anywhere, right? So what that's really saying is, if you think about it, Bernoulli's equation is saying, basically, if we neglect that potential energy term, Bernoulli's equation is just saying that P plus a half rho velocity squared is equal to a constant, okay? And normally that's only true along a streamline, okay? Those two terms only balance to a constant along a streamline in most flows, but if we assume that irrotational relationship, and we know that all our flows are irrotational, actually those two terms are constant everywhere within the flow field. Does that make sense? It's kind of important, right? You didn't, other than for this course, you didn't ought to be applying Bernoulli's equation in any situation that isn't along a streamline, okay? So then what we could do with this half-ranking body is we could just then evaluate that P plus a half rho U squared term somewhere where we know the result, okay? So we evaluate that term far upstream, where we know, or as engineers we should know, what that ambient pressure was and what that free stream velocity was. That allows us essentially to evaluate that constant, and then we can use that along with the knowledge of the velocity field to work out what the pressure field is on the surface of that body, okay? So we just write that P infinity plus a half rho U infinity squared is equal to the pressure at the surface of that half-ranking body plus half rho times this horizontal and vertical component of velocity, okay? And by doing that and rearranging, we could get P minus P infinity, which is a measure, which is really a measure of how that pressure on the surface of that body differs from ambient conditions, okay? So if P minus P infinity is positive, that pressure force is pushing normally onto that surface, and if P minus P infinity is negative, that pressure force is exerting a suction or a force away from that surface, all right? And what we can then do is look at the pressure distribution around that body. And you notice that the pressure's pressing inwards where the velocity is slow, close to the stagnation point at the front of that half-ranking body, and that those blue arrows, that pressure force is kind of acting outwards, so it's exerting a suction, for want of a better word, on the sides of that body where the flow is accelerating, or where you've got this dark red color, which is high velocity. Okay, and we also kind of spoke about how we could just kind of arbitrarily replace other contours in that flow field with a solid boundary. So what we looked at was this example where I replaced that horizontal contour with a solid boundary, and we spoke, or I kind of flapped my arms around a bit and tried to explain to you that that could be a model of the flow over the front of a car or a cliff. And I think the important thing here is to realize that if you get more fancy with these combinations, you can start modeling other things. So we realized if we move that source away from the x-axis and added image features, we could model a vehicle that actually had flow between it and the wall. And if you remove that solid boundary, I kind of suggested that that's also a nice model for a subsonic inlet to a gas turbine. Okay, so we've got this half-ranking body, okay, and it's very simple. It was just two uniform flows summed together, and it's, you know, it's somewhat useful to us, but it's limited, okay. So one problem is that it's infinite in x, okay. So that you know. That half-ranking body, as we've modelled it, actually just continues for infinity in the x direction. That one's pretty easy to solve, but the other problem is that we can't really use that flow to simulate any kind of angle of attack. And you can demonstrate that pretty easily as shown on this slide. So at the moment, we've been considering a uniform horizontal flow that's coming from right to left, which was minus a u infinity y, okay? There's a missing minus sign here. There should be a minus sign in front of this u infinity, in front of this u infinity term for this flow. The more general expression for the stream function for a uniform flow could be written as u infinity y cos alpha minus x sine alpha, okay? And we've been considering the case where alpha is 0, so this term x sine alpha just disappears. But the more general way of expressing a uniform flow is as shown in that expression on the bottom of this slide. So what I can do then is vary alpha. So I've got that uniform flow coming from different directions. But you already know what's going to happen, right? What's going to happen if I change the angle of that oncoming uniform flow? Remember, this is just a source at the origin. Anyone? That's right, okay, because that body's really just that plume, the plume from that source being swept downstream, all right? So if I change the angle of attack of that oncoming flow, I just change the angle of attack of that half-ranking body, which means that it's still at 0 relative angle of attack to the flow. So I still, and it's all right, we'll sort it out in due course, but I still don't have a method of simulating angle of attack on a body with this simple half-ranking approach, okay? And your answer is absolutely correct, right? If you look at the streamlines within the solid boundary, then obviously everything from that source is just being swept in the direction of the uniform flow. So there's really no mystery here to what's going on. All right, so anyway, what we're going to do is solve that infinitely long problem straight away, okay? So the flow comes from the right-hand side, it meets that source, and the flow parts, which gives us the kind of shape for the front of that half-ranking body. So a source parts the uniform flow to create the front of the body. How am I going to close it to stop it being infinitely long? Come on, it's Friday afternoon, so I asked you a dumb question, and it deserves a dumb answer. A sink, right? Which is the opposite, or the kind of, the opposite of a source, all right? So if we place a sink somewhere in that flow with the appropriate strength, then we can just close those streamlines and generate this well, not particularly useful shape, but at least it's got a finite length. It's got a front and a back, okay? And I don't think I'm giving too much away by telling you that that's called a full ranking body, if you really want to get into arguments with people about potential flow. So, full ranking body, which is, it will come up later in today's lecture, isn't on its own that interesting, but this concept of having a source and a sink is very, very useful for us, okay? And actually what it gives us is our next building block flow. We still won't be there in terms of speaking about angle of attack. In order to talk about angle of attack, we have to have some way of adding a circulation. But for the time being, that combination of a source and sink, it gives us another building block flow, which we're going to head towards in today's lecture. So, for now, just consider a source and a sink of equal strength positioned as shown in this figure, all right? So the source is a distance s in the source and sink are both located on the x-axis, and the source is a distance x, s in the positive x direction, and the sink is a distance s in that negative x direction. So they're just positioned as shown here. So, and I can easily write out so no uniform flow for now, just the source and the sink. So I can easily write out an equation for the stream function for this system, okay? And it's just the stream function for a source, which is this first term here. Remember, the stream function for a source is just q on 2 pi theta, and we can write theta in terms of an arctan. So the total stream function is a stream function for the source plus the stream function for the sink, okay? We just add those two together. That negative sign is just there because a sink has the equation for a sink has a minus sign. It's got a negative volume flow rate. It's removing volume from the flow field. Okay, so at the moment I've written that out in Cartesian coordinates, but it's actually probably more convenient to write it in cylindrical polar coordinates. So if you consider some xy position in space, so you consider some point xy, I can write that expression also in terms of these angles theta a and theta b. Okay, so the stream function now is just q on 2 pi theta a minus q on 2 pi theta b. And those angles theta a and theta b are just as defined on that figure. Okay, so theta a is the angle that the point makes, that point in space xy makes with the source, and theta b is the angle that that point in space makes with the sink. Is that clear? As clear as anything is this late on a Friday afternoon. So all I've done here is switch from Cartesian to cylindrical polar coordinates, all right? And I guess I'm just doing that, because I know that it's going to make life simpler for me going ahead. But you've got to be kind of wise to that. When you're flinging around the algebra in this course, there'll be times when you'll probably just hit a wall when you're working in Cartesian coordinate system. If that happens, it's at least worth a couple of seconds just to think about whether switching into cylindrical polar coordinates will make life easier for you. And likewise, later on in this course, there's actually, I won't talk about that. I'll talk about it later on. But for now, I don't want to demoralize you. But for now, switching between Cartesian and cylindrical coordinates is worth remembering. Okay, so this now tells me that the stream function psi is just equal to q on 2 pi theta a minus theta b. Okay, and a line of constant stream function psi is going to define a streamline, all right? So I can just write that the equation for a streamline is some constant c is equal to q on 2 pi theta a minus theta b. So actually, since q on 2 pi is also a constant here. What I'm effectively saying is that the equation for a streamline, or a line of constant stream function, is just theta A minus theta B is equal to some other constant. Okay? So a streamline here is defined by the trajectory of that xy coordinate, where theta A minus theta B is equal to 0. So actually, if you stare at this long enough, you can see that that angle that I've marked in red, alpha, is just equal to theta A minus theta B. So with that in mind, what shape are the streamlines going to be? It is a circle, okay, and I'm kind of impressed that you recognize that. So that comes from this, that comes from the circle theorem, which at one point was probably the only piece of geometry you knew, but it was taught to you such a long time ago. So that's just saying that the inscribed angle within a circle is going to be a constant between any 2 points that are on the circumference of that circle. So, I mean, you can see that. I can show you graphically, right? If I just, in order to keep alpha constant for different, if I vary theta A or theta B and try and keep alpha constant, the only way I can do that is if that point xy tracks out this circular profile, or this circular streamline. So if you couldn't remember the circle theorem, and actually there's some benefit to doing this, you can prove that those streamlines are circular algebraically, and in doing so we get a little bit of extra information about this problem also. And it's worth doing anyway, because it's one of those kind of mystery exercises that was set for you in the PDF notes. And again, there's no solution to this given in the notes, so we'll let these lecture slides serve as a solution to that problem. So psi is equal to q on 2 pi theta A minus theta B, and we can alternatively show directly that those streamlines are a circle. So theta A minus theta B is equal to 2 pi psi on q, and what we can do here is just take tangents of both sides of that equation. And I have to say that that's also a useful kind of recourse throughout this subject if we get stuck with the algebra. So I just take tangents of the left and right-hand side of that equation, and you'll see that on the right, that bracketed term 2 pi psi on q is a constant, right, for a given streamline. We're saying that for any streamline, psi is going to be a constant, and we know that q and 2 pi are constant, so that tangent term on the right-hand side can be expressed purely as a constant, and I'm going to call that A. So just let tan 2 pi psi on q equal A, and then we can just write that tan theta A minus theta B is equal to some constant A. So the next step from there, I guess, also tests your memory of geometry and trigonometry, but you can use this tangent difference theorem. I can rewrite tan theta, the tan of theta A minus theta B, as tan theta A minus tan theta B plus divided by 1 plus tan theta A multiplied by tan theta B. You've used that formula many times before, right? In high school, right? Which is probably, so I'm either really insulting you or I'm just talking about stuff that you've long since forgotten, and it will remain to see which of those is true. So we make that substitution, and again, you've kind of got to be crafty, because at this stage it's useful now to jump back from cylindrical polar coordinates into a Cartesian representation, all right? So we know already that tan theta A is equal to y on x minus s. You can see that very clearly from this diagram, right? The tan of theta A is just opposite over the adjacent. So the opposite is this distance y. The adjacent is this distance here, which is just x minus s. And likewise, we can write that tan theta b is equal to y on x plus s. So if you plumb all of that into that difference theorem at the top, it looks initially like everything's just getting worse and worse. But when you gather those terms together, you'll see that that equation actually simplifies very nicely to this form shown on the slide. And then with a little bit of rearranging, we can get this expression shown here. And you know the equation for a circle, right? The equation for a circle just tells me that x minus x naught squared plus y minus y naught squared is equal to some constant, and that constant is the radius of the circle squared. So what we can do is just rejig that expression that we have into that form, okay? We can rewrite that equation in that form, and you see that the equation for the streamlines associated with a source and sink are just going to be, those streamlines are just going to be circular. They've got no offset in x, so the center of those circular streamlines is going to be located on the y-axis. They're offset in y by this distance s on a, and they have this radius squared as given by that constant on the right-hand side of this expression, all right? So it's up to you. You've either got to remember circle theorem, or you can prove, actually, I've made a meal of this. You can prove quite simply that those streamlines associated with this, a source and a sink, are circular, okay? So if you have a source and a sink, those streamlines are going to be circles. Those circular streamlines pass through the center of those sources and sinks. And we know that that offset of the center of that circular streamline is going to be this distance s on a in that expression that we just derived. And we know that the radius is going to be the square root of the right-hand side of that expression that we just derived. Okay, so it's going to be s square root 1 plus 1 on a. Okay, and remember I can't remember what a was, but it was the tangent of something that involved the stream function, okay? And we're setting the stream function to a constant value in order to find the equation for a streamline. So every different value of that constant value of the stream function psi is going to give rise to a different circular streamline as given by that equation. Okay, so if I plot those streamlines for many different values of the stream function, you can see that streamline pattern associated with this source and sink. Okay, and it's just this weird superposition of all of these circular streamlines. Okay. All right. So now let's add flow from. So that's not just useless algebra that we've been doing, right? It's going to become useful for us soon. Hopefully by the end of this. Hopefully by the end of this lecture, if I hurry up. So now we're going to add a flow from right to left. So I'm just adding a uniform flow from right to left, and I'm gradually increasing the strength of that flow relative to the strength of that source and that sink. And you see that you get this the shape that we've already know we're going to get, which is this full ranking body. Okay, so forget about those circular streamlines just for the time being, and let's just analyze this full ranking body in the way that we've kind of been learning how to analyze these flows. Okay, so what should I do? Kind of walk me through what my approach should be if I want to understand this flow kind of if I want to understand the topology or the shape of this flow or what makes it tip. I've got an equation for the stream function. That's easy, right? It's just a uniform flow plus the source and the sink. What would you do if you were me? You'd just give up. It's always an option. Yeah, all right. First step, I think, would be to find the velocities, okay? So that's easy. That's just a differentiation of that equation for psi. Again, you've got to be able to differentiate arctans. I hope you're getting the impression that you're going to fail at the first hurdle if you can't do that, all right? Differentiating the uniform flow is very easy with respect to y. That minus u infinity y just becomes minus u infinity. And likewise, for the v component, just take a minus psi and differentiate that with respect to x. So an interesting thing that I forgot to mention up to now is that because that uniform flow from right to left it has a stream function that's minus u infinity y, when we differentiate that with respect to x, it just goes away, okay? So actually the vertical component of velocity v knows nothing about that uniform flow. You can see that very clearly in the algebra there. So that uniform flow has no influence on that vertical component of velocity. It only appears in the horizontal component for this uniform horizontal flow that we're simulating at the moment. All right, so we've got u and v. What's the next step? Stagnation points, okay? I'm sure I heard one of you say that, and it's not just wishful thinking on my part. So stagnation points are when u and v are both equal to 0. So I'm going to be lazy. I don't want to just solve that set of simultaneous equations. What's the shortcut? Actually, you can just stare at that expression for v. What's the easy? What line in the flow should I be looking for those stagnation points on or along? What? Yeah, y equals 0, okay? And it's very obvious from the algebra, from that equation for v, but it should be equally obvious from the axis of symmetry in that flow. There's this axis of symmetry at y equals 0, and you know on that axis of symmetry there's going to be no war normal, no v component of velocity. So if we look along that line, we automatically know that v is equal to 0, and then all we've got to do is find a position along that x-axis where u is also equal to 0. So we can substitute y equals 0 into that expression, and then we've got the equation for the variation of u along the x-axis, along that line where y is equal to 0. So it looks like a bit of a mouthful, but you can see that those terms cancel out. Some of those terms in the square bracket cancel out in a pleasing way, and I can just gather I can gather those two terms that are subtracted within that square bracket together also in quite a nice, algebraically, in quite a nice way. So all I'm looking for are situations where u infinity is equal to that term on the right here. And you see that I can just rearrange this expression to get an equation. I can rearrange this very easily to get an expression for x. All right? So it might not show from my very smooth delivery, but I haven't taught this course for 4 years, all right? And I'm coming back to these slides that I made 4 years ago. So for some reason, I solved that equation using the quadratic equation. I'm not sure what state of mind I was in when I did that. But actually, yeah, b is just equal to 0. So I really didn't need to go to such lengths, right? I could have just, I don't know what I was doing. You don't need to resort to quadratic equation. Maybe I was just being thorough, just in case b wasn't equal to 0. But anyway, there's an easy solution to that to that expression, okay, which is going to give us the location of the stagnation points surrounding that source and that sink with the uniform flow. So the stagnation points, and none of this is surprising because I've sketched the flow for you anyway, I guess. But this is a kind of process that you go through if you didn't know what the flow looks like. So those stagnation points are located, one just upstream of the source and one just downstream of the sink, those tiny red dots that I've put on this slide. So what next? Yeah. So we find the separatrix. So what do we do? So separatrix is a streamline, right? So it's a line of constant stream function. So the first thing we should do is find what that constant is, which is, for the flows we're looking at, is actually often quite trivial. So you go back to that equation for the stream function, and now you just substitute in those coordinates that we found for the stagnation points. And I don't have to get fancy here. I don't need to substitute in x. You can immediately see that when I substitute y equals 0 into this expression, the stream function's just going to equal 0. Okay? So all I'm looking for is a line of constant stream function where the stream function is everywhere equal to 0, and that will be the equation of the separatrix. So again, it's very straightforward. I just set that stream function equal to 0, and I solve or try to simplify that expression to give me an x coordinate as a function of y, or vice versa. So again, I think it's easier in cylindrical polar coordinates, so I'm going to rewrite arctan y on x minus s as theta a, and that other arctan term as theta b. And again, well, I'll test you, all right? So I want to get an expression of x versus y. So what would you do next? Well, I'm really testing your memory here by like 10 minutes or so. So I guess a convenient way effectively of switching between Cartesian and polar is sometimes to take tangents of both sides of the expression, which was what we did previously to prove that those streamlines for the source and sink were circular. I guess that's another good tip if you really get stuck. So, and actually all we're doing by doing that is trying to get rid of those arctans in that Cartesian form of that expression, I guess. So you take tangents of both sides of this equation, and again, there's quite this nice, simple result. I can rewrite that tan theta A minus theta B term in terms of that tangent difference theorem. We've done all of this before, right? I can substitute back in what tan theta A and tan theta B mean in terms of x and y, and then I can poke that back into that equation that we had at the top. And at that stage, and all I'm doing here is nothing's changed. That we've just got a 1 on that tangent term, which has become that cotan. Okay, so now you're kind of there. You've got this expression for that separatrix, this weird oval-shaped separatrix that we get for that half-ranking body. And it's not particularly informative, all right? It's not a perfect ellipse. It just tells us that that half-ranking body, if you're good at, it tells us that it's going to be some. It's pretty obvious that it's going to be some closed profile, I guess, and perhaps it's obvious to you that it's going to be roughly some oval shape. So that separatrix, if I plot that equation in MATLAB onto this figure, that separatrix is just this red line shown on this figure. And just to show you or really just to persuade you that this isn't all complete nonsense, we can compare that to the flow field that we'd get around a similarly shaped body if we released dye in a flow. So I have to say this is a very, very low Reynolds number flow, a kind of creeping flow of fluid around a half-ranking body. So what they've done here is they've created a solid body with the shape given by that equation that we just derived, and then they have this very slow flow of liquid around that body, and they release dye at certain points into that liquid, and that dye will track out streak lines, which in a steady flow are the equivalent of streamlines, and you can see that that pattern around that shape is very close to the pattern that we were finding from this analysis, from this 2D inviscid incompressible analysis. So, as I've said, that shape is called a full-ranking body, not very originally named. But it does give us a kind of starting point to introduce this concept of a doublet. So, just as an aside here, all right, what we have at the moment is the flow coming from right to left. And the source is mounted upstream of the sink, as we've sketched it here. So the direction of that uniform flow obviously is critical, okay? If the flow came from the other direction, then you get a completely different flow topology. And I'd suggest that you treat this as a kind of problem that you could go away and nut out if you have some spare time. So this is exactly the same, a source plus a sink, but a uniform flow coming from the other direction. So u infinity y rather than minus u infinity y that we've been considering previously for the stream function. So you get this very complicated flow, but if you analyze it in exactly the way that we've shown you to analyze those half and full ranking bodies, you should be able to find where those stagnation points occur within this flow. And what you'll find is that the flow topology is completely dependent on this ratio u infinity s on q. If it's small, if it's less, or to be precise, if it's less than 1 on pi, you're going to get. Can you see my pointer on the screen, okay? Not very well, I guess. If it's small, you'll get one stagnation point up here and another one down here. And actually, you've got this weird region of reversed flow here, where basically you're saying that the source and the sink are so strong that this sink is just sucking the flow from that source back upstream. So you've got this flow reversal occurring locally. And then if I keep increasing the size of u infinity on S, eventually you get this solution with only one stagnation point, which is when u infinity S is equal to 1 on pi. And then if I keep increasing it, you get these two stagnation points that now occur on the x-axis as given by this equation. So very complicated behavior, but if you just follow through that process that we went through with that full ranking body, I think that you'll easily be able to nut out those solutions. So I would suggest you kind of treat this as an exercise or a tutorial problem where at least you've got the solution and check that you can find your way to that solution. It's just the half-ranking body, sorry, just the full ranking body with the flow coming in the other direction. Okay, so we've got this full ranking body. It's a kind of semi-useful, semi-streamlined body, I would say. At least it's no longer infinite in x, but we've still got this same angle of attack problem. If I now add flow coming from an angle of attack, it's even worse, I would say. We've got this horrible mashup that occurs, I guess. You still effectively swing that body around with the direction of the flow, and at some point you just end up with something that looks like that, somewhat like that half-ranking body with this extra sink kind of growth on the side of it. So it's hopeless, right? It's not going to give us, it still doesn't give us the ability to look at angles of attack, but we do have a closed, at least a closed geometry for that body. Okay, so anyway, the kind of the punchline, I guess, to all of that agony is to take that full ranking body and see what happens when we move that source and the sink ever closer and closer and closer together. Okay, so remember that the source was a distance s upstream of the y-axis, and the sink was a distance s downstream of that y-axis. So what I want to do is consider this case where s asymptotes to 0, all right? And you've forgotten it because it was many minutes ago now, but we derived the equation for that red oval shape, that separatrix for the ranking body. And you can kind of stare at that equation. And what I'm doing here is S is going to tend towards 0. So these two terms are going to tend, these two terms here are going to tend towards 0, all right? So that equation is going to tend towards x squared plus y squared. X squared plus y squared is going to tend towards 0. So what do you reckon is going to happen to that? As I bring that source and sink together, geometrically, what do you reckon is going to happen to that shape of that oval? It's going to disappear. That's a very good point. All right, it's definitely going to disappear when that source and that sink are co-located. They're going to cancel out. So that's true. But as it's tending towards that kind of vanishing point where it disappears, what's that geometry of that separatrix going to asymptote towards? A circle, right? And it's kind of, I guess it's kind of obvious just by staring at that figure. When I bring those two together, I'm going to reduce that major axis of that kind of oval type shape. So as I bring them together, you can see that that separatrix gets smaller and smaller, but it does kind of tend towards being a circle, okay? But I can't, if I co-locate my source and my sink, at least in my MATLAB program, it's just going to, the separatrix is just going to disappear or vanish, okay? So maybe this is an unfair question, but what could I do to stop it disappearing or vanishing as I brought the source and sink together? Pardon? Make the stronger. Yeah, absolutely, all right. So where this S on the right-hand side is going to asymptote to 0, but if what I could do is make the strength of the source and sink very strong, okay? And then I could make it so that cotan term asymptoted towards infinity, okay? So what you do is, what we're going to do is now as we move the source and sink closer together, we're going to increase the strength of the source and sink so that strength is just equal to some constant, which I'm calling K, divided by S. Does that make sense? So as S becomes very small, if K is a constant, then Q is going to asymptote towards infinity, okay? And I guess I hate asymptotics, all right? But I guess what it's saying is that S is going to asymptote towards 0 slower than that cotan term asymptotes towards infinity, all right? So what you see is that and all I'm doing is implementing this now in MATLAB. I've set that Q for the source and the sink is equal to some constant divided by S, and then I'm just going to move these flow features closer together, okay? So those s's go to 0, this term's going to go to infinity, and you can see that as I bring that source and sink together, the x squared plus y squared is asymptoting towards a constant, okay? And you can see that that shape of that separatrix now is asymptoting towards a circle, okay? Which makes sense because x squared plus y squared is tending towards a constant. And obviously in my MATLAB program I still quite co-locate that source and the sink, otherwise something nasty is going to happen with the way that MATLAB handles in infinity. Does that make sense? That's a good question, and we'll get to it now, in fact, okay? You can kind of get a sense for it hidden behind the source and sink there. There's this weird kind of double circular pattern of streamlines within that separatrix that we'll see in just a moment. But I guess I always feel like this part of the course feels like smoke and mirrors, but there is a rationale for doing this. We end up with this very useful building block flow by bringing a source and sink together in that fashion. So this kind of co-located source and sink is known as a doublet, and it's going to be our next building block flow that we're going to make use of. And obviously I need an expression for the stream function for that doublet, and we can quite easily write that expression out. And I think I can do it in the 3 minutes or so that I've got remaining. All right. So yeah, if you're asleep, just wake up now for 3 minutes, and then you're free for I take it, probably for the weekend. So consider that source and sink. I can write out that equation for that source and sink, which is just psi equals q on 2 pi theta a minus theta b, okay? And as we saw before, I could also write that stream function was equal to q on 2 pi alpha, where the angle alpha, shown in red, is just theta a minus theta b. So what I want to do is rewrite alpha in terms of this new angle theta, as shown in red here, and theta is just the angle that point xy in space makes with the origin of my axis system. Okay? So that distance between the origin and x comma y is this distance r, and I can also try to define some, through geometry, I can also define some other lengths on this figure that I'm attempting to sketch here. So I'm going to call these two lengths, these triangles that are made, I'm going to call these two lengths LB and LA. And remember that we're considering this scenario where the source and sink become very close together, so where S becomes very small, okay? So as S becomes small, you can all see that angle alpha is going to become small, yes? So I'm going to be able to make use of the small angle approximation. And the way that I've sketched those distances LA and LB, there's right angles close to the origin as shown on this figure. But as alpha becomes very, very small, I can make this approximation that these other two angles are also going to be tending towards right angles, but only when alpha becomes very small, when S becomes very small. So with that in mind, and using this small angle approximation, I can just write that. Can you even read this on this figure? You can see LB and LA on the figure. So with that in mind, I can just write that LB is going to tend towards S sine theta, and LA is going to tend towards S sine theta. Is that clear? Just from geometry? So what I can write is that angle alpha, and again this is just a small angle approximation. By the small angle approximation, that angle alpha will just be equal to the tangent of that angle alpha, which I can approximate as just that distance LA plus LB divided by that distance r. So I can say that alpha is going to asymptote towards LA plus LB divided by r, which is just 2s sine theta divided by r. And now all I've got to do is plug that back into my equation for the stream function, and I can just write that the stream function for the doublet is just equal to qs sine theta on pi r. Okay? So you remember that I said that qs is a constant. You remember that I set the strength of the source and sink equal to a constant divided by s. So qs is just equal to a constant. So I can finally just write that the stream function for a doublet is just k sine theta divided by pi r. Okay? So this is our next building block flow that we're going to be considering. And it's called a doublet. And I'll show you the flow pattern associated with a doublet on Tuesday. But it's essentially... what is it, essentially? It's a co-located source and sink of infinite strength, but that, I think, doesn't help you understand what it is. Looking at the flow pattern of the doublet on Tuesday's lecture is probably what's going to help, but you'll be pleased to hear that I'm out of time for now. So.
Source in the same location in a simplified model of the black hole. Nothing comes out. Everything, light from it, the heat from it is like stacking. And if the U infinity is slow enough,
I think that's true. If there's no U infinity, then I think everything that comes out goes back in.
Yeah.
Yeah. I think that's true.
Okay, just jump in.
I think that's true. But yeah, you're right. But the thing is, I think it's also true for a source and sink that even with a finite distance between them, with no uniform flow, no, it's not true. It's not true.
Because we consider special location in the x-axis.
Yeah.
The source still can go out.
That's right.
Which means if you find the right angle, you can still observe like this.
Yes.
But the series will come inside out.
Yeah. So I guess for the doublet, you're saying even on the doublet, even along the x-axis, there's no escape of the. I think you're right.
It's become more and more interesting.
Yeah, I think you're right. Okay.
Actually, you missed a square somewhere in the slides.
Pardon?
A square you missed to type actually.
The S.
And the S plus A square actually.
Oh, okay. I missed a squared term. Okay, I'll look back at that. But
actually, I want to ask you something else. Like, I was applying for an internship.
yes.
So they need some reference. Like,
Yeah.
Can I give you?
Yes. Yeah.
So
Sure.
they need the first name, last name, and the mail ID and contact number.
Yeah. So I think you can get all of that off of the. Just find an expert page on the university website. Mm-hmm. So it will have my contact number and full name and address there. Okay. So I'm happy to do it, but probably you might be better to choose someone for a reference. Is this your first semester at Mel?
Second.
Yeah, you might be better to choose someone where you've already done a course with them and done well.
I sent them mail like, but they are not
They
replying.
haven't replied. Yeah. So
and today is the last day. So.
yeah. Then use me. Yeah.
Thanks, man.
I believe this is the model you have just mentioned here.